We are now going to deal with osmotic pressure and Van 't Hoff factor. Osmotic pressure is the pressure required to stop the water molecules from passing through a semi-permeable membrane. So you can calculate the osmotic pressure, given the molarity of solutions and all that. The Van 't Hoff factor is slightly different. This is supposed to be for ions, and Van 't Hoff factor states that not all ions are going to be ionized. And so you have to calculate a Van 't Hoff factor for that. Okay, so if you have two ions in a solution, so for example, if you had NaCl, they should technically give you sodium plus chloride. Okay, so which means two ions. So, but sometimes that does not happen. Okay, and so the osmotic pressure that you end up getting may not come from two ions, but maybe 1.98 or 1.8. Okay, so that is something that you can also calculate. So we'll be doing those two calculations on this page. So the first question, very simple, straightforward. Calculate the osmotic pressure of a 0.05 molar magnesium sulfate solution at 25 degrees Celsius, and I, which is the Van 't Hoff factor, is given to us. Okay, so generally this is the formula for calculating osmotic pressure. So pi, which is osmotic pressure, is equal to I mRT. I is the Van 't Hoff factor, M is molarity, R is gas constant, and T is temperature. So if you're going to use the gas constant, which is in all the standard units, you make sure that your temperature is also in the standard units. So 25 plus 273 is 298 Kelvin. Okay, and so then the Van 't Hoff factor for magnesium sulfate is given as 1.3. So as I was just explaining to you about the Van 't Hoff factor, magnesium sulfate means that you have two ions in there, but see, you're not getting the pressure from two ions, you're getting the pressure from only 1.3 ions. So anyhow, the 1.3 times 0.05 molar solution times 0.0821, and that is the same gas constant we used before, liters, atmosphere, mole, Kelvin, times 298, which is in Kelvin. And so this cancels out, Kelvin cancels out, and then we are left with 1.6 atmosphere. Okay, so that is the osmotic pressure that is caused by 0.05 molar magnesium sulfate. Technically, it should have been 2 over here, because if you had two ions, then this I should be 2 technically, but that didn't happen. All right, let's look at the next problem now. Calculate the Van 't Hoff factor of sodium phosphate in 0.4 molar solution whose freezing point is minus 2.6. So this is how we will calculate the Van 't Hoff factor. Now the previous problem was using the osmotic pressure, this one is using freezing point. So the Kf of water is given to us. Now Na3PO4, technically speaking, should give us 4 ions. Okay, so technically speaking, it should change by 4 times, but that doesn't happen, right? That's why we're doing this calculation. So our formula for freezing point depression is TF, and the only change that we do when we have ions in there is you use I factor, Kf, and then the molality. So this is the difference in the formula when you have ions in there versus when you have substances that do not dissociate, like sucrose, glucose. They will not dissociate at all. Okay, so in that case you just have the 1 over here, so we never have to use I, but for ions it's a little different. So we are calculating the Van 't Hoff factor over here, so which means that I is equal to delta TF divided by Kf and then the molality. So pretty straightforward over here. The change in the freezing point is 2.6 degrees Celsius. Kf is already given to us, which is 1.86 degrees Celsius over molality, and then the molality is also given to us, which is 0.40 molar solution. Sometimes you may have to do these calculations, but in this case at least everything is given to us. Okay, and so then the answer for this question is 3.5. And so that tells you that instead of having 4 ions, having the effect of 4 ions, you're actually having the effect of only 3.5 ions, because the dissociation of sodium phosphate is not complete.